Hello and welcome. Today, we're looking at how we can tackle rising greenhouse gas emissions by turning CO2 into something useful. One promising technology is called super dry reforming, or SDR. SDR focuses on CO2-rich gases, especially those with methane, and converts them into syngas. That's a valuable mixture of hydrogen and carbon monoxide used in chemical production. What's really interesting about SDR is its ability to handle feed gases with much more CO2 relative to methane, even up to 3 CO2 molecules for every methane molecule. This is a big deal for utilizing industrial off-gases or CO2-heavy biogas. There have been some exciting breakthroughs. One involves using solid oxide electrolysis cells, or SOECs, in a high-temperature process. This electrothermocatalytic approach combines methane dry reforming, the reverse water-gas shift reaction, and water electrolysis right at the SOEC's cathode. Water, which is a byproduct, gets electrochemically reduced to produce hydrogen. This process essentially drives the equilibrium to favor higher CO2 conversion and hydrogen production than you normally expect. Catalyst development is also a crucial part of these advancements. For example, scientists have created catalysts by exsolving rhodium nanoparticles onto a cerium dioxide support. This creates special active sites where methane is broken down, and CO2 is absorbed and activated. This same setup also helps with the electrochemical reduction of water, significantly boosting CO2 conversion. In fact, systems using these advanced catalysts and SOEC integration have shown methane conversion rates of 94.5% and CO2 conversion of 95% when using 4 parts CO2 to 1 part methane, producing almost pure carbon monoxide and hydrogen. Beyond electrocatalysis, chemical looping concepts for SDR are also progressing. These systems typically use a nickel-based reforming catalyst, an oxygen carrier like iron oxide, and a CO2 sorbent such as calcium oxide. In this cycle, methane and CO2 are reformed to syngas. The syngas then reduces the oxygen carrier, and the CO2 is captured by the sorbent. Later, the oxygen carrier and sorbent are regenerated, releasing concentrated CO. This method theoretically allows for the conversion of up to 3 CO2 molecules per methane molecule, though making these materials robust and cost-effective for industry is still a challenge. Another significant hurdle in methane reforming is carbon deposition or coking, which deactivates catalysts at high temperatures. Researchers are working hard on coke-resistant catalysts. This includes designing them with strong metal support interactions, using bimetallic combinations like nickel-cobalt, or creating core shell structures. For example, molybdenum-doped nickel nanocatalysts on defect-free single-crystal magnesium oxide have shown excellent coking resistance over long periods. The potential impact of successful super dry reforming is substantial. It offers a direct route to transform CO2-rich gases from industrial processes or biogas into key chemical building blocks. This not only helps reduce greenhouse gas emissions but also paves the way for sustainable fuels and chemicals, promoting a circular carbon economy. Future progress will depend on improving catalyst durability, scaling up these processes, and integrating them with renewable energy sources for widespread industrial adoption. That's all for today. Thanks for listening.